I've been playing with microcontrollers to make stuff like to make like my keyboard. I like microcontrollers. I was looking up stuff on microcontrollers. Oh, I wanted to get good at music. So my wife is basically a music streamer. She streams as Spork of Love, Space Cat that plays music. Man, I love doing stuff with her. It's the best. But I'm bad at the musics. I've got a MIDI interface. I've tried making music. I've put songs together, but not in real time, right? I can't do it in real time. But I wanted to play music with her somehow. And so I was thinking the real problem is the interface to all these musical instruments. I spent like a day sitting down with a ukulele and I'm garbage at it. I couldn't get my fingers to do the things to make the notes. And I'm realizing all these notes and stuff, they're hard. You got to think through where all the things are, and the systems of division, how they're set up to make the chords. It's really complicated. It didn't have to be complicated. It's just math. So if it's just math, I can get a computer to do it for me. So I started thinking, what can I do that makes the noise? And it turned out a lot of people are making synthesizers with this particular microcontroller, which I've worked with a similar stuff before. So I just decided one day that I wanted to do this and ordered the Teensy, not knowing anything about how I was going to design any of this, and just look stuff up. This is the Synthulele. It's like a ukulele, but it's a synth. Yeah. Right. It does all kinds of music. It's got a little speaker on inside, but you can also jack it into things and, put it into I've got an amp down there. But basically, I made this because I suck at playing any kind of instrument. I've tried playing string instruments. I've tried doing all kinds of things, and they're not designed for me, right? Even a piano is built dumb. What did they do? Look at this. Here. Look what they did. But this is not a normal, but you get the idea. These keys, why are these up here? Why did they do that? Why make all these different? What are these separations for? That has nothing to do with music, mathematically. It doesn't make any difference or change. It's silly. So I made this thing to work the way I work, which is that each of these is a step up from the last one. This row and this row are an octave up from each other. And then you can shift octaves up by these things. So and I mean, I would never want to play chords like that because that's just silly. So instead, these keys up here automatically play chords for you. So this is major, minor. I don't remember what this one is. Diminished, major seventh, minor seventh, and dominant seventh. So I can play pretty much any song, and if I need to, I can do. There's different key codes for pressing multiple for really weird chords that I almost never use. So it automatically plays the chords for you. This is not a lead instrument. I think of this more like a bass, like it's something you play along with another instrument to kind of as a backup. So I'm not playing fancy I'm not shredding on this thing. Although you can a little bit if you want to. If I got good at it, maybe. So I studied how chords are built, how the math of notes works, the work, all of it, and I put it into the code that you can see over there. And this is programmed on a Teensy 4.1. It's a very fancy little Arduino-like microcontroller. Oh, I'm doing this in the wrong way. I can load this up into Visual Studio. I forgot. That'll make this whole thing way easier. Oh, yeah, that's way better. Okay, so math-wise, the octave value and this are super important for calculations going forward. I don't remember how I derived those, but I know that I did a lot of like looking up how math for music works. Music math, all of music is based on math. Very, very cool. So the more I learned about that, the more I was sure that I could do a music. There's this. This is the audio system design tool for the Teensy. Basically, I have a ton of waveforms coming in, a ton of envelopes, and then they all get mixed down and then potentially put through a bit crusher, potentially put through a chorus, and also potentially put through a flanger, which I ended up putting in eventually. And then I output them through the medium quality sound output on the Teensy. You have to connect it to pin 12 or 10 for it to come out. It is not as good as any kind of like audio DAC or something that you could wire into the Teensy to get good music out of it potentially, but it does work. Yeah, it says it right here. Yeah. Better than pulse width modulation, but not as good as a proper DAC or audio shield. Yeah, it works good enough for the kind of 8-bit sounds that I wanted to get out of this thing. So yeah, I found this thing, and it outputs a chunk of code that looks like this. All this. See, look, GUI tool and automatically generated code. And I eventually ended up going in here and heavily editing this. So instead of the automated stuff that got put in here, these patch chords, virtual patch chords, code patch chords, I ended up making all the waveforms and envelopes into arrays. So that way you can see I put each of the different waveforms and things in here. That's just so I can like manipulate them easier. Creds. Creds are my version of chords. We'll get back to those later. I got the stuff set up for the LCD here. These are ints for the little knobs that are on there. This is for the rotary encoder. I got these little up, down, and the button press. These are the pins that each of these are plugged into, and that's what these are too. These are the pins for the LCD. These are the pin numbers on the Teensy. So that's what a lot of this is for, setting up where the hardware is. I found these two. These are libraries for setting up rotary encoders and debouncing switches. And I tried a ton of these kind of things until I found ones that worked well for what I had. Oh yeah, this is like the lead pin that's on the lead that's on the Teensy is always set to pin 13. So if you use pin 13 for something else, then you don't get the lead anymore. This is just a variable to hold on to what waveform I'm outputting to all the waveforms. You could do like square waves and sine waves and triangle waves and things like that. Next part is the keyboard matrix. So exactly like my own mechanical keyboard that I made, on the back you get this keyboard matrix, and you get wires running across this way and wires running across this way, and you hook them up with little diodes on each of the keys to make so the current only goes one way. And through that matrix you can pulse pieces on and off and detect where the output comes through, and that will let you know which key is pressed. So basically I have this row and column matrix, and I assign those to various numbers. So I have these other row column matrix areas that I use to I've got a string for each of the notes, and I've got a note offset for each of the notes, or for each of the keys. So each of the keys has a letter assigned to it. Remember I said that the bottom row and the top row were the same notes, but off by an octave, and that's where they are here. And so this is how much, what note number they are. So you can see these are basically a sequence with A starting at 0, and then I subtract notes to get the G sharp and G, and then we add a note to get the A sharp, and then a 2 for a B, 3 up for C, and so on and so on. So as I press a key, it associates that key with a numerical value to tell me how far off from 0 my note is. Yep, I got stuff for arpeggios in here and for timings. This is set up for the chorus effect and the flange effect. And then we start just getting the actual code into like how we're setting up the whole thing. This sets up the key matrix. Look, I've got some, look at that. Look, I put documentation. This sets up the LCD column and rows for the, and it's supposed to output Synthulele here, but it screws it up. I don't know why it does that. It like overwrites some of it. Maybe we'll figure that out as I go through this. This is for the arpeggio. This is for the rotary encoder button. This attaches the bounce for the rotary encoder. This turns on, this sets up the LED. This is an amount of audio memory that needs to be set up for the audio library that I'm using. Yep, sets my current waveform to square. Oh, this sets up all of my waves and envelopes to have the right data in them for starting off, for when it starts up. So it just goes through this is one of the reasons that I put all the waves and envelopes into an array instead of just having them just be their own variables, is because otherwise I'd have to do this for every single one of them. And that sounded nightmarish. So we put them in a loop. Set up the bit crush effect, set up the chorus effect more. Begin the chorus sub effect thingies. Begin the flange. Oh, let me know that I got to the end of setup. And that's good. That's it. These are variables for figuring out chords and octaves and things like that. It looks like my octave starts at 4. Okay, so here is the note calculation stuff. But it sends in a float, which is the frequency, and it multiplies it by my octave. So I have my starting 27.5 times however much I want to multiply the octave, and then it does this. Okay, so this is the octave, whatever we get out of this, times magic to the power of my note. So magic was this weird number here, and I found out this. I did a lot of math to figure out what that number needed to be and how to do this calculation. I don't remember any of it now. I'm wondering if I left it in as a comment, like, hey, here's how you figured that out. Nope, it's gone. It's gone into, like, I'll never understand that again. It sounds like, to your ear, that every note is just a step up from each other note. But physically, that's not the case. If you look at the actual frequencies of the notes, it is doing a doubling, not exactly a doubling. It is doing some kind of multiplication. There it is. So this is the exponential growth of the different notes. And that is because, oh, and look, there's my 27.5 to the power of X. That's the code for okay, I found it. Found that. That right there, that calculation is for getting this curve, which goes back to my octave at 27.5 and my magic number, which is how I got because this calculation is always the same. The secondary one, 2 to the X, is that number. Cool. So this is setting up The frequency comes in here. Octave multiplier gets set elsewhere. That's controlled by those the 2 octave shifting buttons. Then we do the calculations to find out what the actual frequency of the note is. Okay, yes, this is update my cruds. Cruds are my version of chords. It's called on any note press or hold. So it gets updated as you hold a key. And I send a crud structure into this. Let's peek my definition of this. Indexes to wave envelopes. Okay, so these numbers, A, B, C, D, are potential wave envelopes, which means they're single frequency note things that can be played. These are Booleans that I don't remember what are for. Okay, cool. Chord is set elsewhere, so we're doing a switch based on what chord is currently being pressed. So that's the top buttons on the thing. These floats are the frequencies that we're going to put into the crud, into the wave envelopes, I'm pretty sure. So we go through it, we pick out what chord we're playing. So here we're not playing any chord. So that means that we only need one note. And we're sending the key num. C.key num is from the crud. Okay, so the key number is, yes, on the crud. Okay, so the key number is those, remember that first matrix that was next to the, it's basically what button you're pressing on the note matrix. It's the offset in value for the note that we're going to play. So we get that and we send it into this note calculator, goes through all the magic math and offsets it based on its offset to 440 times the octave we're on. And it outputs a frequency that we can use in all kinds of stuff. So I make sure we're doing a chord of none. The fourth note is definitely waltz. And then this selects the different cases. So for major, minor, we do calculations for each note's frequency based on what, because every chord is a structure of distances between different frequencies. And if I know what those are, I can pull off any kind of chord. So this is all the settings for all the different types of chords that this can do. Then I turn on this thing that's no audio interrupts. But you need to turn it off, and then you need to turn it back on. I know that much. And you want to do that, I think, while you're making changes to audio stuff that you want to all happen at the same time. So I think that's why that happens. Okay, so we do another, if chord is 0, we're doing a single note. That goes from here to here. So this is if we're doing a single note, then we turn off each of the envelopes that are not. So if this in case we're switching from pressing a chord to pressing a single note. We turn off the other chords or the other notes in a chord. Not playing the fourth note, then we need to turn off the last note in the chord. If my first key is a -1, my first index of wave envelopes is a -1. In other words, I think that means I've put it into not being a wave envelope because there's no -1 in the index of wave envelopes. Then I eat that. So this is all a cache. That's what the wave envelopes act like. They act like a set of available notes that can be played. And so this is a system for cycling those in and out of existence, right? I grab 3 wave envelopes from the array and I use them to play a chord. But I could be playing a second chord, or a second chord could be fading out while I've played the next chord. And those would be grabbed out and played for that. And then when I release those, I set them back into the into like a pool of wave envelopes that I can use for either single notes, arpeggios, or whatever. So this is a cycling system to kind of like put those back into the pool or take them out. So like here you can see I'm always setting one of my indexes to the first frequency because I'm always at least playing one note, and then I'm checking whether I'm doing arpeggio or not, and then doing timing for the arpeggio stuff, or if I'm just doing like normal code things, then we're turning on the other notes. Complicated, crazy things, whether I'm doing arpeggio or not, and whether or not I'm playing different chords and stuff. There's a bunch for ending chords or cruds. This next note is for doing arpeggio stuff. Yep, I select different cases based on which step in the arpeggio I'm on, and I just up that one at a time, and I play those sequentially, and basically ups this counter, and figures out which note it should play, and whether or not it should play a fourth note or not. And if it gets to 5, it goes back to the beginning, or if it doesn't have a fourth, it goes back to the beginning. We put it back to 1. This is all the code to check the key matrix. I'm not going to give a tutorial on how to do a keyboard matrix. There's probably information somewhere else out there that would be better than what I'm doing. Basically, I did make my own keyboard matrix reader that directly interfaces and controls turning on chords, updating them, and setting them. And this is basically, it's just a keyboard, except that instead of outputting letters to computer, it turns on the music. Key was being held down, so as I'm holding down a key, I'm updating the chord. This is stuff I don't remember writing. Yeah, okay, so here's the stuff for the octave multipliers, right? Basically, I'm using these key codes here that I put into my own little matrix way up here. Right, so in the key matrix, I've got these really high numbers and these really low numbers. These numbers are my note offset. And if my value from what key's being pressed is higher than 100, then I register it as a special key. So basically I'm going through, and this is how I calculate all the key presses, how I increase and decrease my octaves, turning chords on. When I release, I need to end my chords, which ends up eating those indexes for the wave envelope arrays and putting them back into circulation. Yeah, that's all the key presses. This writes things to the LCD in a way that it cannot be understood. I have to make sure that there are 20 characters that get set to each line on the LCD. If I don't, it won't erase stuff from the last send to it. So I need to make sure that that's what this does, is it finds the length of the string that I'm sending to the LCD and adds another 20 space, or adds up to 20 characters of space at the end so that it can print it out properly. Oh, maybe this is why the Synthulele thing fails, is I'm not actually using this to send to the, yeah, that's probably why. Maybe I should do that. Okay, this is the menuing system that lets me add different effects and change the different waves. Basically, I am just using the button press to cycle through. This is just a standard menu system. Yeah, it's how I click through. It changes all the displays on the LCD. It changes the flange depth and delay and frequency. This is how much bits are being crushed and things like that. And clicking through and incrementing the different waveforms, which are basically on an index. This is the actual like numbers that need to go to the waveform generators. And these are the kind of waves that are in there, plus or minus through them, based on whether or not, you know, press forward or backward on the rotary encoder. Oh, here's the main loop. Inside the main loop, we update the menu. We have a timer here that checks. Right, the Teensy runs really fast, like really, really, really fast. So I make sure that I'm only checking the keys every millisecond, because if I do it too fast, it breaks big time. It starts, just the signals jump all over the place. That's one of the things I found out running this, is that the Teensy's like stupid fast. It runs at 600 megahertz. That's a lot of times per second. So I don't understand why that didn't work, but you had to slow this thing down. Otherwise, it was not happy. It caused all kinds of weird errors and jumbles of things. So I made sure I slowed it down. It only happens once per millisecond, not like 600 times per millisecond or whatever. It checks the keys. Every update, apparently you need to begin the waveform. I don't know why that is. That's just how the audio library works. So this updates the LCD all the time with what octave, what chord, and what key are playing. So I can actually look down on the display and figure out what notes I'm pressing. This reads all the potentiometers for the chorus. This sets all the release and attacks based on IC and ID. So these last ones set the release and attack for the notes. Arpeggio time is set by IA. That's that analog one. If menu selection. I guess if I'm not in a menu, it goes through and updates these values for attack, release, chorus, and arpeggio. Oh yeah, this sets the chorus right here. Okay, that's setting the chorus, that knob. We do a read for the arpeggio switch and turn that on or off. And we turn a light on. If this ever turns on, which I'm sure it does for somewhere. I just turn it off. That light doesn't go on anymore. Interesting. I probably should hook that back up. That was cool. And that is it? That's all of it. We're at the bottom. We went through everything. Did that explain everything? Probably not. But I have done what I intended to do, which is to click through all this and kind of show how the insides worked a little bit. Hopefully I'll be able to turn this into a video that you are watching right now on YouTube. If you have any questions, come over to twitch.tv/robottelevision and you can ask me when I'm streaming or leave a comment down below and I will try to answer it. I'm a professional internet entertainer.